we are going to start the chapter 9 of class 9th mathematics, areas of parallelograms and triangles. So we have divided this chapter in two lectures. So we will start our first lecture with some basic definitions related to these topics. The first definition we have, it is the planar region. So planar region means we are talking about that a simple closed figure is there. We are talking about this figure, and the region that is enclosed in between this region we are talking about, that is enclosed in between this boundary, that is the planar region. And the magnitude of the or the measure of the planar region enclosed by the figure, that is called the area. The magnitude or the measure of the planar region, that is area, is just a number we are saying that how much area it is occupying. Next is congruent figures. So two figures are said to be congruent if they have the same shape and the same size. As we have seen in case of triangles, congruent basically means they are just identical, that if we put one on the other or we superimpose one on the other, they are exactly the same. Next we have some axioms related to that are called the Euclidean area axiom. First is existence postulate. So we are saying that if a polygon P is there that lies in a plane, then it has an area. This thing is represented over here, that there exists a real number area of P. This thing we are saying that, suppose I am talking about this is some plane over there, we are saying this is the plane P. So area of P is always greater than equal to 0, and this area of P is some real number. This always exists. If some region is there, then it will have some area. This is the first axiom we have. Second is the dominance postulate. Dominance postulate means that if we have two regions and one is the part of another, we are talking about this is one region, this is R1, and this is another region, this is R2. We are saying that area of this larger region, suppose it is A1, and area of this smaller region is A2. Then we are saying that R2 is contained in R1. This is basically the symbol for subset, but you do not know much about the set theory. So in case of subset, you can just read it like it is a part of. So we are just saying this is a part of. So we are saying R2 is a part of R1, then area of R2 is less than area of R1. We are saying A2 will be less than A1. Next is postulate of additivity. So we are saying for any two plane regions R1 and R2, such that this thing now means, we are talking about this condition over here, this thing means that this is the symbol for intersection. Intersection basically means that the regions, they are non-overlapping regions. This is the symbol for union. Union means we are adding those two regions, we are adding the area of those two regions. So we are talking about that, suppose this is first region, this is the second region, this is R1, it has area A1, this is R2, this has area A2. So we are saying if we consider the area of R1, union means you can just think it as or R2, then it is just the sum of these two areas. That is, we are talking about the area of both these figures. We are talking about the area of both these figures. Then we are saying that the total area will be A1 plus A2. So it means if we have two different shapes or two different regions which are non-overlapping, one has area A1, second has area A2, then the total area will be A1 plus A2. Same thing is represented over here in this figure. We are saying we have one figure A, B, D, and second we have it is D, B, C. The first one A, B, D, it has area R1, and the second one has the area R2. The second one has the area R2. then the total area of this region will be R1, area of R1 plus area of R2. Now the next is congruence postulate. So we are saying if R1 and R2 are two congruent figures, then they have equal areas. Congruent figure means they are the identical figures. We are suppose this is the region R1 we are saying, and suppose we are talking about the congruent means identically same region. We are saying that there is another region, this is R2, this is region R2. Both these regions, these are congruent to each other, they are identical, they are same means if we overlap one region on the other, they will overlap with each other, or they will superimpose on each other. Then we say that both these will have the, if this has the area A1, this will also have the area A1. But we are saying if two figures have same area, it is not necessary that they are congruent or they are identical. We do not use the word identical mathematically, we use the word congruent. Same we are saying. So for this case, we have given the example over here that we have considered a square A, B, C, D. The sides of the square, they are of length 4 cm each. Then we have considered a rectangle P, Q, R, S, and the sides of this rectangle are 8 cm and 2 cm. Now area of this square is 4 into 4, that is equal to 16 square centimeter. Area of this is 8 cm into 2 cm is equal to 16 square centimeter. But if you will superimpose both these, then it will be just like this. Suppose I put one on another, it will be A, B, C, D. We are saying these two figures, these are not the congruent figures, but they have the same area. Now the next we have, next is the figures on the same base and between the same parallels. So we are saying we are given two figures and the base for both the figures that is same, that is they have a common side that we call as a base. Suppose I am talking about this first figure, I am talking about this triangle ABC. Suppose this is one triangle, and second I am talking about ABD. These two triangles we are saying. So they have a common base means they have a common side over here. This side AB is the common side. Now the second condition we have is, we are saying they have the same base. Same base is clear that we are talking about that they have a common side, that we are saying they have the same base. And the next thing we have is, and the vertices opposite to the common base of each figure lie on a line parallel to the base. We are saying the vertices opposite to this means we are talking about the vertex C and vertex D. We are talking about these two vertices and they lie on a line which is parallel to the base. We are talking about this line XY is there, and both of these vertices, they lie on this line XY, and this line XY, this is parallel to AB. So this is the case of triangles. I am again explaining over here. We are having one triangle, we are saying this is A, B, C. Second triangle we are talking about is A, B, D. We are saying we have this AB as the common base over here. This is common to both these triangles. We are drawing a line over here, the CD. The CD line and AB line, these are parallel to each other. Then we are saying that these two figures, they lie on the same base AB and lie between the same parallels AB and CD. In the second example we are talking about, this is a parallelogram ABCD. We have considered another parallelogram ABEF. We have considered this parallelogram also. Both these parallelograms, they have this common base AB. This AB base, this is common base. And we are talking about a line over here. This line we are saying, this line is the common, the parallel line we are talking about. This is these two lines, these are parallel to each other. So we are saying that these two parallelograms, the parallelogram ABCD and the parallelogram ABEF, they have the same base AB. They have the same base AB and they are between the same parallels A, B and D. These are the two parallel lines. Next is we are considering the trapeziums. In the next example, we are talking about the trapezium. One is ABCD. This trapezium we are saying. And second, we are talking about the triangle, that is ABN. We are talking about this triangle. Now, we are saying they are lying on the same base. This is the base AB we are talking about. They are lying on the same base and they are lying between the same parallel. Now, the parallel line we are talking about, it is DN over here. This is AB over here. So, these are the two parallel lines and this is the same base we are talking about. Next, we are talking about these figures. In the first case, we are talking about the triangle ABC and the triangle ADE. If we are talking about these two triangles, this is our length AB over here. This is a line we are talking about, that is XY line. We are saying these two lines, these are parallel to each other, and both these figures, they lie between the same parallel. But now what problem we have over here is that this triangle AB, when we are talking about, it has the base AB, and when we are talking about the triangle ADE, it has the base AD. So these two triangles ABC and ADE, they are between the same parallels but not, it is important over here, but not on the same base. Next is we are talking about the parallelogram ABCD. This is the parallelogram ABCD. And second, we are talking about the triangle PBQ. This is we are talking about this. This is the third figure we are talking about. This is about the second figure. So we are saying parallelogram ABCD is there. This is ABCD is there. And we are talking about the triangle PBQ. Again, both of these, they are between two parallel lines, but they are not on the same base. Similarly, ABCD. Third case, ABCD is the parallelogram. PQRS is the parallelogram. These two parallelograms, they are neither on the same base, but they are between the same parallel. These are the parallel lines in which they lie, but their base is not same. So these are some of the examples from which we can distinguish between the figures, that how they lie on the same base and between the same parallel lines. Next, we are talking about two triangles over here. One is the triangle ABC and second is the triangle ABP. We are talking about these two triangles. Now what we have is both these triangles, they lie on the same base AB. But if I join these 2 points C and P, what I will see is I am joining these 2 points C and P. These two lines, these are not parallel to this A, B and C, P are not parallel. So we get that these two triangles ABC and ABP, they are on the same base, but they do not lie between the same parallels. Similarly, we are talking about the parallelogram PQRS, and the second we are talking about is PQMN. This is the trapezium. So both of these have the same base. This is the common base they have, PQ. We are talking about this is the same base they have, but they are not between the same parallels. Next, we are talking about one is the square RSTV, and second we are talking about is RSPQ. So this is RSTV is a square and RSPQ is a parallelogram. We are saying both of these, they lie on the same base. Both of these, they lie on the same base RS, but they are not between the same parallels. These two figures, they are not between the same parallels. The next result that we have is that two parallelograms are given to us which have the same base and they are between the two parallel lines. Then we have to prove that they have the same area. So this is an activity given to you, that is explained to you, that you can try at your own. That you have to draw a parallelogram A, B, C, D, and then you will draw another this A, B, C, D we are talking about. Then you have to draw another parallelogram, that is A, this one we are talking about, that is you can say A, B, E dash E, or you can say A dash E dash E, and you will come to know that the area of both these parallelogram, they are same. The procedure is explained over here and you can try this at your own. Now the next thing we have is that we are going to prove this result, that parallelogram on the same base and between the same parallels are equal in area. So we are talking about two parallelograms. One is A, B, C, D. This is one parallelogram, and second we are talking about is A, B, E, F. These two parallelograms, they have the common base over here. This is the common base, and these two lines DE and AB, they are parallel to each other, so they are between the same parallels. Now we have to prove that their area, they are same. So we are considering the triangles. The one triangle we are talking about, it is AFD. This triangle, I am drawing it over here. This is AFD we are saying, and the second triangle we are talking over here, it is CEB. This is ADF and this is CEB. Now in these two triangles we have AD is equal to BC. We are talking about these sides AD and BC. These two sides, these are equal to each other because we are talking about this AD and BC. These two sides, they are equal to each other because they are sides of a parallelogram. Suppose the length of this AB is X, length of this DC is X, and length of this FE is X. Suppose we are talking about this length Y over here, this DF and CE, both these lengths, suppose we are saying this is Y and this length is Z over here. So what we get from this is, we are talking about a line. This line we are saying, this is the point D, this is the point F, this is the point C, and this is the point E. What we are saying is that this length DC, it is X, and the length FE, it is X. This length is also X. We are saying this length is suppose Z and this length is suppose Y. So what is the value of this whole length I am talking about? If I have to calculate the length of DE, I can calculate it like from this one. So the value of DE is X plus Z. Second thing I can do is, I can add this much length is X and this much length is Y. So we are saying this is equal to X plus Y. X gets cancelled, so we are left with Z is equal to Y. Z is equal to Y means we are talking about this length DF and this length CE. Both these lengths, these are equal. We are saying this length DF and this length CE, both these lengths, these are equal to each other. Then the next thing we have is, if we are looking at these two, this is AD line and second we are talking about is BC, this BC. Then we have the transversal, this DC over there, and we are saying that these angles over here at this D and this angle over here at C, both these angles, they will be equal because these are the corresponding angles. So we are saying this angle D is there and this angle C is there. Both these angles, they are equal because these are the corresponding angles. These are the corresponding angles. So by SAS axiom, we are saying both these triangles, these are congruent to each other. Now if both these triangles these are congruent to each other, it means their area is also equal. The area of both these triangles, it is equal. So we are talking about this figure over here, that is A F C D. We are talking about this figure. Suppose the area of this figure, we are saying this is some quadrilateral A B C F. We are adding to this quadrilateral this triangle over here. We are talking about this triangle, we have added to this quadrilateral. We are talking about this triangle. Then this quadrilateral becomes the parallelogram. This point is E over here. This becomes A B E F. So we are saying that the area of parallelogram A B C D, if we are talking about, this is A B C D. The area of this parallelogram A B C D, that is equal to area of triangle ADF plus area of quadrilateral ABCF. Similarly, the area is, this is equal to area of triangle BCE plus area of quadrilateral ABCF, and that is equal to area of triangle parallelogram ABEF. Basically what we are saying is that if we look at this figure over here, then this ABCF, I'm talking about this region ABCF, this is common to both of them. We have added a triangle on this side to get one parallelogram. We have added a triangle on this side to get the second parallelogram. And as the area of both these triangle it is same, so area of both the parallelogram it is also same. Similarly, this result can be written in this form. We are saying this is a special case that a parallelogram and a rectangle on the same base and between the same parallels are equal in area. Next thing we have is base and altitude of a parallelogram. So the first definition we have, it is base. So we are saying any side of the parallelogram can be considered as a base. If a parallelogram is considered, you can consider any of the sides as a base. Next is the altitude. It is the length of the line segment which is perpendicular to the base from the opposite side. So we are talking about any parallelogram ABCD is given. If suppose I am saying I can consider any side as the base. Suppose I am considering BC as the base. Then altitude means we are talking about that we have to draw a perpendicular from this D to this BC. We are saying this is the point M over here. This is the perpendicular that we have drawn. Then this DM, this is called, this is BC is the base, and this DM is the altitude. Similarly, we are talking about AB is the base, and this DL is the altitude over here. Now the next result that we have is that the area of the parallelogram is equal to the product of its any side and the corresponding altitude. So we are saying, suppose a parallelogram ABCD is given to us. We are considering AB is the base of this parallelogram, then AL will be the altitude. Then the area of this parallelogram will be AB into AL. You can consider AL as the altitude, you can consider also BM as the altitude. Altitude is basically, we are saying height. It is just as in case of triangle, it is height over here. So you can measure the height from any point on AB. So to prove this, we are going to draw BM. We are considering over here that this AB is the base and this AL is the altitude. Now we are saying we are going to do the construction, that is BM is perpendicular to DC, so that ABML is a rectangle. We are talking about this figure. It is ABML. This figure we are talking about. This is a rectangle. And we know that the area of this rectangle is AB into BM, or it is AB into AL, that is length into breadth. Now the next thing we have is that both this rectangle ABML and the parallelogram ABCD, they both lie on this base AB, and they both are between the parallels A, B and L, C. These two are the parallel lines. They both lie between these two parallel and they have the same base. So the result from the previous result we have is the area of the rectangle ABML, that is equal to the area of the parallelogram ABCD. So and that is equal to AB into AL. Now in this next question, we have to prove that parallelograms on equal bases and between the same parallels are equal in area. So we are talking about two parallelograms. One is ABCD and second is PQRS. It is given that their base AB and PQ base, they are equal and they lie between the same parallel line. This is DR and this is AQ we are talking about. If we look at this parallelogram, it is AB and DR. This is PQ and DR. These are the two parallel lines we are talking about. So to prove this, we are going to do the construction over here, and the construction is that we will draw the perpendicular from A to DC, from P to this DR we are talking about. This is the line over here. We have drawn the perpendicular on this, and we know that these two lines we are talking about over here, that is A, B, P, Q and DR. These two lines, these are parallel to each other. So these two distances, the length of these two lines, we are saying they will be equal. That is, we are saying AL is equal to PM. Both these distances, they will be equal. That is, the distance between two parallel lines, it is equal at every point. So when we have to calculate the area of this parallelogram, it is AB into AL. We will calculate the area of this parallelogram, it is PQ into PM. This is base into perpendicular, base into perpendicular. What we have is this AL and PM, these are equal to each other. So we get that the area of both the parallelograms, they are equal. Now the next question we have, a diagonal of a parallelogram divides it into two triangles of equal area. So we are given a parallelogram ABCD and we have to prove that the triangles we have over here, this ABD and the second we are talking about is BCD. Both these triangles, these have equal area. So when we are talking about these two triangles, we are saying this side AB and this AB and CD, they are equal in length. Then AD and BC, they are equal in length. And third side BD we are talking about, it is common between these two triangles. So both these triangles, these are congruent to each other. If these are congruent to each other, we know that congruent figures have equal areas. So what we get is that the diagonal of the parallelogram divides it in two triangles that have equal area. Next question, we have to prove that triangles on the same base and between the same parallels are equal in area. So we are saying that we have a triangle ABC. This is the triangle ABC. And the second triangle we are talking about, it is DBC. These two triangles we are talking about. We are given that this BC is the common base over here and this line is there. And these two lines, these are parallel to each other. BC and EF, these are parallel to each other. And we are saying both these triangles, they lie on the same base and they are between the same parallels. So we have to prove that their area, they are equal. So to prove this, we are going to do the construction over here, that we have drawn this BE line, this BE parallel to AC, and this CF, this is parallel to BD. So what we get from this is that BC and ED, these are parallel. BE and CA, these are parallel. So we get this figure we are talking about, BCAE. And second we are talking about is BCFD. This is the second figure we are talking about. Both of these are the parallelograms. Both these parallelograms have the same base and they lie between the same parallels. So it means that they have the equal area. Now when we look at this parallelogram over here, BCAE, this BA is the diagonal. We are talking about this parallelogram BCAE. We are saying BA is the parallelogram. So if the area of the parallelogram is A, then the area of this triangle we are talking about, if the area of the parallelogram is A, then the area of this triangle will be A by 2 and the area of this triangle will be A by 2. Similarly, when we are talking about the parallelogram BCFD, we are talking about this parallelogram over here. We are saying this CD, this is a diagonal. So what we get is that the area of this triangle we have, it is A by 2 and area of this triangle is A by 2. Because area of the two parallelogram, they are equal and we are considering that the area of parallelogram is A, then area of each of these triangles we are talking about, it is A by 2. So what we get is that the area of triangle ABC and area of triangle DBC, they are equal, and this is what we have to prove. Now the next thing we have to do is we have to prove the formula for the area of the triangle. That is, the area of the triangle is half base into height. So we are talking about a triangle, say ABC. To find the formula or to derive the formula, we are saying we are going to do the construction over here, that we have drawn from C a line parallel to AB, and from A we are drawing the line parallel to BC. The point where both of these intersect, we are saying this point is D over here. So now the opposite pair of side, we are talking about AB and CD, they are parallel. BC and DA, they are parallel. So what we get is that this figure BCDA, this is a parallelogram. Now to find the area of this parallelogram, we are constructing the altitude AL over here. This is the altitude. The area of this parallelogram will be BC into AL. Now this AC will be the diagonal for this parallelogram. If this is the diagonal, so what we get is that the area of this triangle and area of this triangle, area of both these triangles, they are equal. It means area of this triangle is half of BC into AL, and this is what we have to prove, that the area of triangle is half base into height. Now next question we have, that if a triangle and a parallelogram are on the same base, we are talking about a triangle over here, that is ABC, and a parallelogram, that is BCDE. Both these figure, these are on this is the same base and they lie between the same parallels. Then we have to prove that the area of this triangle is half of the area of the parallelogram. So we are saying this AL is the perpendicular for this altitude for this triangle, and this DM is the altitude for this parallelogram, and both these AD and BM, these lines, these are parallel. So what we have is that the length of both these altitude AL and DM, their height we are saying, or their altitude, they are equal. Now if we write the area of this triangle, it is half base is BC into height is AL, and if we write the area of this parallelogram, it is base, that is BC, and height is DM. This is the height over here, this AL is the height over here. Then what we get is this AL and DM, these are equal. Suppose they are equal to x. So this is area of the triangle is half BC into x. This is BC into x. So what we get is the area of the triangle. Now area of triangle ABC, that is equal to half area of triangle, the parallelogram BCDE. Now we have, if two triangles have equal areas and one side of one triangle is equal to one side of the other triangle, we are talking about two triangles, one is ABC and second is DEF. These are the two triangles we are talking about, and we are saying that one of their side they are equal. Suppose we are talking about this side BC, this is equal to EF. We have to prove that their altitudes, they are equal. So if we write the area of this triangle, it is half. Suppose this length over here, it is x, and the altitude of this is A1. We have this length is x and altitude of this triangle is A2. So area of this triangle is half x into A1 and area of this triangle is half x into A2. Next we have is both the area, these are equal to each other. We equate these two equations. We get half x into A1 is equal to half x into A2. Half gets cancelled, this x gets cancelled, and we are left with A1 is equal to A2, and this is what we have to prove, that their corresponding altitude they are equal. Next we have to prove is that the area of the trapezium, this is the formula we are talking about, it is half sum of the parallel side into distance between them. So we are saying that we are given a trapezium in which this side BC and this DC, these are parallel to these sides, these are parallel to each other. So we have to find the area of this trapezium. To find the area of this trapezium, we have drawn AC, that is we have drawn the diagonal over here, this AC we are talking about. Then the trapezium is divided in as two triangles. One is the triangle ACD and second is the triangle ABC. These are the two triangles we are having. To find the area of these two triangles, we have drawn the perpendiculars. This is for this triangle, we have drawn that perpendicular over here, that is this AL is the perpendicular. We are saying its value height is h. For the second triangle, we have drawn this perpendicular over here, that is MC, its height is h. Now the area of this triangle will be, the base is DC, height is h, so it is half base into height, and the area of this triangle is half, the base for this triangle is, this is the base AB, and height is h. Now the area of this whole trapezium will be sum of these two values, this value and this value. The sum of these two values is the area of the trapezium, so it is half DC into h plus half AB into h. This is equal to half of DC plus AB into h. This is sum of two parallel sides and h is the distance between the two parallel sides. This is what we have to prove. Next we have to prove is the area of a rhombus is half product of the diagonals. So we consider the rhombus over here, it is AB, CD, and we have diagonals over here, that is AC and BD. We know that the diagonals of the rhombus, they are at 90 degree to each other. So if I consider this triangle, I am talking about ABC. So for this triangle I am saying this is perpendicular over here, this is AC, and this is the perpendicular OB. So the area of this triangle will be, this is the base, OC is the base, so it is half base into height is this OB. Now consider this triangle, we are talking about this triangle over here. This is ACD, this is perpendicular over here, this is the point O. We are saying this length we are talking about, this is AC is the base, so area is half AC into OD. So we are talking about, this is the area of the upper triangle, this is the area of the lower triangle. So the total area will be sum of these two, it is 1 by 2 AC into OD plus 1 by 2 AC into OB. So what we get is 1 by 2 times AC common, and it is OD plus OB. Now what is OD plus OB? This is DB. So the final formula we get, it is 1 by 2 into product of the diagonal. AC is one diagonal and BD is the second diagonal. Next we have to show that the line segment joining the midpoint of the pair of opposite sides, suppose we are talking about this parallelogram is given to us A, B, C, D, and we are saying that this E and F, these are the midpoint of the opposite sides. If this length is x, then this length is x by 2, this is x by 2, x by 2 and x by 2. Suppose the height we are talking over here, that is h. Anywhere you can draw the perpendicular, the height is h. So what we get is that the area of this parallelogram AEFD, that will be x by 2 into h, base into height. Area of this parallelogram will be x by 2 into h, and both these area, these are equal. So we are saying the line drawn from the midpoint, it divides the parallelogram in two equal parts. Or you can directly use the theorem that we have already proved. We are saying the base of these two parallelograms, that is AE and EB, we are talking about, this is the base, the one base is AE and second is the parallelogram base is EB. Both these base, they are equal, and these parallelograms lie between the same parallels. So what we get is that the area of both these parallelograms will be equal. Next we are given a parallelogram ABCD. This ABCD is a parallelogram. We are talking about the diagonals. One diagonal is AC and second diagonal is BD. They intersect at the point O. This is the point O where they intersect, and a line segment is drawn passing through O, and it meets this AB at the points P and Q. We have to prove that the area of the quadrilateral APQD, that is the shaded portion over here, that is half the area of the parallelogram ABCD. So to prove this, we are saying that the diagonals of the parallelogram, they divide each other in they divide this parallelogram in the two triangles having the equal area. So we are saying this triangle we are talking about ABC, the area of this triangle ABC, that will be the half of the area of the parallelogram. This is area of triangle ABC, that will be half the area of the parallelogram ABCD. This thing we know. Now we consider the two triangles. One is the triangle OAP. This is OAP we are talking about, and second is the triangle that is OCQ we are saying. So in these two triangles we have these two sides, these two angles, these are equal to each other. Then this angle and this angle over here, these are equal to each other, and these angle at A and C, these are equal to each other. Next we know that O is the midpoint of AC, so both these sides, that is this OA length and OC length, these are equal to each other. So both these triangles, these are congruent to each other, so their area will also be same. The area of the triangle we are talking about APO, I think the area of this triangle OAP and OCQ, they are equal because both these triangles, these are congruent to each other, and congruent triangles have equal area. Now we are talking about the quadrilateral AOQD, that is AOQD. We are talking about this quadrilateral first. If we add the area of triangle OAP to it, we are talking about this area OAP to it, we are saying that is equal to the area of triangle, this area of this triangle, that is equal to the area of the triangle, the second triangle we are talking about, that is OCQ, plus the quadrilateral AODQ. So what we are saying is that the area of this region, this is equal to the area of this region. Now the area of the triangle ACD and ACB, they are equal. So if the area of these two triangles, they are equal, we are talking about the area of the triangle ACD and the area of the triangle ACB, both these areas, they are equal. The area of this triangle ACD and APQD, these are equal. So finally what we get is that the area of the quadrilateral APQD, that is equal to half the area of the parallelogram ABCD. Why? We are using this result, that area of the triangle ABC, that is equal to area of triangle ACD, that is equal to half the area of the parallelogram ABCD. Next we have to show that the median of a triangle divides it into two triangles of equal area. So we are talking about a triangle ABC over here. The median of the triangle means this is the point D. So both this AB and this DC, these are equal. If we draw a line over here that is parallel to this BC, we are talking about, we have drawn a line over here that is parallel to this BC, then we are saying we are having two triangles now. One is the triangle ABD and second is the triangle ADC. Both these triangles have equal base, their base, they are equal, and they lie between the same parallels. So it means both these triangles will have equal area, and this is what we have to prove. Now we are given a triangle ABC. We are talking about, this is a triangle and AD is the median. AD is the median means we are talking about this BD and DC length, these are equal to each other. Then we have to P is any point on this AD, and we have joined this BP and PC. We have four triangles over here. One is this triangle, second is this. We have to prove the area of these two are equal. Next we have is this triangle and this triangle, and we have to prove that the area of these two triangles, they are equal. So the result that we already know is that the median of the triangle, it divides the triangle in the two parts that have equal area. So if we talk about the triangle ABD and ADC, they will have equal area. We are talking about area of triangle ABD, that will be area of triangle ADC. This is ABD and second is ADC. Both these triangles, they have equal areas. Now we are saying that P is any point over here. Then for the triangle PBC, we are talking about, for this triangle we are saying this PD is the median over here, that is D is the midpoint over here. These two sides, these are equal to each other. So D is the median for this triangle. We are talking about the triangle PBC. D is the midpoint over here, so PD is the median. It means the area of these two triangles, these are equal, that is area of triangle BPD, that is equal to area of triangle PDC. So this is one part we have already proved, that area of these two triangles, these are equal to each other. So if we subtract both these equations, we get area of triangle ABD minus area of triangle BPD, that is equal to difference of these two. Now what is this area? This is the area of this upper triangle, and this subtraction, after subtraction, this will be the area of this triangle. So we get that the area of these two triangles also, that is BPB and this APC, the area of these two triangles are also equal. Next we are saying that a triangle ABC is given to us. This is a triangle ABC and D is the midpoint of BC. This D is the midpoint of BC and E is the midpoint of AD. This E is the midpoint of AD. We are saying these two lengths are equal. We have to prove that the area of the triangle BED, this BED, that is 1/4 the area of the triangle ABC. So if we look at this triangle ABC, we have this D is the midpoint over here. It means AD is the median. So what we get is that the area of this triangle ABD, that is half the area of this triangle is half the area of the triangle. Suppose the area of the triangle ABC is say x units, square units. This is area of triangle ABC. Now area of triangle ABD, that is equal to half of x square units. Why? Because D is the midpoint over here. It means AD is the median. Now look at the triangle ABD. For this triangle, E is the midpoint. If E is the midpoint, it means this line BE is the median. If this is the median, it means the area of these two triangles are also equal. So what we get is that the area of the triangle BED, that is equal to half the area of triangle ABD, that is equal to half of x, that is equal to 1/4 times x. X is the area of the triangle ABC, and this is what we have to prove. Next is a quadrilateral ABCD is given to us. This is a quadrilateral ABCD, and it is given that M is the midpoint of AC. We have joined these two points A and C, and M is the midpoint of AC. So we have to prove that the area of the quadrilateral ABMD, we are talking about this quadrilateral over here, ABMD, the area of this quadrilateral, that is equal to area of the quadrilateral, that is DMBC. Area of these two quadrilateral, they are equal to each other. So we are talking about that this AM and MC, these are equal in length. So if we look at the triangle over here, this ACM, what we have is that the area of this triangle AMB and the area of this triangle MCB, both these area, they are equal. Now similarly, why? Because this M is the midpoint over here, this M is the, these two lengths are equal, so this MB is the median. Similarly, this DM is the median over here. So what we get is that the area of this portion DMA and the area of this portion ACM, the area of both these portions, they are equal. We are saying these two areas, they are equal. We are saying these two areas, they are equal. Now if we add these two means we have written this over here, that area of AMD is equal to this, area of AMB is equal to area of BMC. If we add these two equations, what we get is this area and this area gets added up. So both these area will constitute this much portion over here. This is the portion we are talking about. And when we will add these two areas, when we will add, we will get the portion this. And what we have is that these two areas, this area and this area, areas are equal. Now in the next question we are given the triangle ABC. We are given a triangle ABC and we are given the three medians over here. One is AD, second is BE, and third is CF, and these all median they are intersecting at the point G. We have to prove that the area of this portion AGB, then AGC, and this third GBC, all these three triangles they are equal in area. To prove this, we start with this, that the area of this triangle ABC we are talking about. For this triangle ABC, this AD is the median, so we get that the area of this portion over here, that is ADB. If the area of the larger triangle it is say A, then the area of this triangle will be A by 2, and the area of this second triangle ADC we are talking about, the area of this triangle will be A by 2. Next we are considering this triangle over here, that is BGC. For this triangle BGC, we are saying this GD is the median, so we divide it into two triangles. One is this triangle and second is this triangle we are talking about, and both of these triangles these will have equal area. Suppose the area of this triangle it is A1 and the area of this triangle it is A1. Their areas are equal. Now look at these two triangles over here. We are talking about that the area of the triangle, this much portion we are talking about. I am marking it again over here, that we are talking about BGA area. If suppose the value of BGA area it is A2 and the area of AGC it is A3. So what we have is, we are talking about these two areas. One is this AGB area and second we are talking about is AGC area. We are saying this area is A2 and this area is A3. So what is the total area ABD? Total area ABD is A1 plus A2, and that is equal to this total area A1 plus A3. A1 gets cancelled, so what we are left with is A2 is equal to A3. So this is our first part we are talking about, that the area of this BGA and area of this AGC, both these area they are equal. This is what we have to prove in our first part. Similarly we can prove the second part, that the area of AGC and the area of CGD they are equal. So if all these three areas they are equal, suppose and these values they are equal to, say we are saying it is A2, then the area of all these three they are equal to A2. So their sum is, we are saying A2 plus A2 plus A2, that is equal to total area A. So we get A2 is equal to 1 by 3 times A, and this is what we have to prove in our last part. Next we have to prove that the diagonals of a parallelogram divides, it is dividing this parallelogram in 4 triangles we are talking about, and we have to prove that the area of all these 4 triangles it is equal. So to prove this we are considering this triangle ACB first. For this triangle, suppose the area of the parallelogram it is A. We are saying the area of the parallelogram that we are considering, the area of the parallelogram is A. Now this diagonal AC, it divides it in 2 parts. One is this part AOC and second is this part ACD. Now area of this part is A by 2 and area of this part is A by 2. Now look at the triangle over here. This is ABC we are talking about. The area of this triangle is A by 2 and this AO, this is the point over here, and we know that the diagonals, they bisect each other. It means this BO is the median for this triangle, this side AC, this triangle ACB. So it means the area of both these, this much portion, area of this portion and area of this portion, they are also equal. So what we get is that the area of this and area of this, the total area of this portion was A by 2. So area of both these portion will be A by 4. Similarly, the area of both these portion will be A by 4. So what we get is that if the total area of the parallelogram is ABCD is A, then we have 4 triangles AOB, BOC, COD and DOA. All these 4 triangles have the area A by 4. And this is what we have to prove, that the diagonals of the parallelogram divides it in 4 triangles of equal area.